In the last lessons, we learned how to calculate for the equilibrium constant, that is K equilibrium, and sometimes just represented by just K, okay? And then we have Kc of concentration, we have Kp for pressure, and Ka and Kb, but in the end they are just K, and they are used for different purposes. But the way to calculate equilibrium is the same process. That is, we have product over reactants. And that is always the same pattern for all the K's up here. Now in this case, we are going to look at a more advanced problem with the calculation of equilibrium constant. There are two things that you need to keep in mind. The first one is that equilibrium constant will always stay the same, and the only time that the equilibrium constant change is that the temperatures change. So only a temperature change will change the values of equilibrium constant. And the second one is dealing with the changes in terms of x. And if you remember last time, we looked at the ice table, right? Ice. And we look at the C in terms of changes in terms of x, as well as the equilibrium in terms of x. But here's the beautiful part. If the equilibrium is small enough that it is less than 10 to the negative fifth, you can actually ignore the x. And because the change is so small, that's the reason why. So keep that in mind, okay? If the equilibrium K is less than 10 to the negative fifth, you can ignore the x in your math. So let me show you how does it work. Well, here we have ammonia decomposed into nitrogen and hydrogen. And of course this is a balanced chemical equation. And what we have here is that it has an equilibrium constant values, that is your KEQ right there, of 2.0 times 10 to the negative 7, which we know is less than negative fifth. Okay, so we can ignore the x. Let's see how that could work. If 3.0 moles of ammonia is placed in a 3.0 liter container and allowed to reach at equilibrium, notice it's not 1 liter anymore, and we have mole, so we have to solve it into molarity. Okay, so what is the concentration of hydrogen and nitrogen? Well, we always start, when it comes to equilibrium, we always start with the ice table. So I have I for my initials, and C for my change, and E is for my equilibrium. So what we have here is, of course, this right here is in mole, but when we express in terms of the ice table, it has to be in terms of concentration. But we can find that for ammonia, which is NH3, it has 3 mole in a container of 3 liter. So what we can have here, of course, 3 mole over 3 liter. What would that give us? Of course, that gives us the molarity of 1, okay? Or we just write 1.0 to keep the consistency of sig-fig. So that's how you figure that out. What about at the beginning of the chemical reaction? Do we have any of the product at all? Of course, no. We only have our reactant. We put in the chemical reaction, and then we have 0 product. Okay? And then for the changes, of course, for the reactant, those products would be lost in the process or used in the process. We have minus 2x because of coefficient right there. And over here, the product will be forming in the process. We would plus x because the coefficient is 1. But over here, we would be plus 3x because the coefficient 3 right there. Okay? Now at equilibrium, of course, we have the combination of initial and the change. So for the equilibrium, we have 1.0 minus 2x, where for nitrogen it's just x, and for hydrogen it's just 3x. Okay? Now this is where it's going to get tricky. Okay? Remember I told you that if the equilibrium is less than 10 to negative fifth, you can ignore the x. What does that mean? See how the changes here? Right there, right? It is a combination of this and that right there. And how is that going to work is that it will only apply to this. Because in the end, this is what makes the math more complicated. This is a variable x by itself. So this is where we will ignore the x if it is less than -5. So since the equilibrium is 2.0 times 10 to the -7, that's a lot smaller than 10 to the -5. So of course you can now cancel it, which means we just have 1.0. Okay. Now let me show you how it's going to work in terms of the calculation. Notice we are only giving the k, right? But we know that k EQ or k equilibrium is equal to N2 H2 to the power of 3, okay? And that is relative to the reactant, which is NH3 to the power of 2. But we can actually substitute this in. Well, for now, we have x and x to the, or 3x actually, 3x right here to the third because of the coefficient right here as well, okay? And that's being divided by, if I were to plug this in, 1.0 minus 2x right there. Do you see how this becomes really complicated because of 1 minus 2x? So because of the equilibrium is this one here, because of the equilibrium is less than 10 to the -5, you can just ignore that part. I forgot to put to the second power. Now as you can see, if we have 2 to the second power, that makes this math very complicated. But if we can ignore the x, what do we just have? We just have this part right here. This part right here will be just 1.0 to the second power, which just equal to 1.0. And that's the beauty of knowing this little trick right there. Okay. So in the end, what do we have? We have k equilibrium, which is equal to 2.0 times 10 to the -7, and that is equal to x times 3x to the cube, and that is divided by 1.0 right there, right? Because we already take to the second power already. Now, of course, that's just 1, so we can just ignore that. Okay, beautiful. Now, what's next? Of course, x times 3x to the cube, that will give us 27x to the 4th. Because this right here, 3 times 3 times 3, that's what it is representing. And x times x times x. And that's how we have 27 times x to the 4th. And that's equal to the equilibrium times 10 to the -2nd. Now do you see how important it is to memorize this trick? Right? Because if we don't apply that trick, the math becomes more complicated. And you have to solve using the quadratic formula. And that becomes very messy. Okay? And then the rest is solving for x is extremely easy. Of course, we are going to divide both sides by 27. Both sides by 27. Okay? So let's use our calculator. 2.0 exp -7 divided by 27. Give us 7.41 times 10 to the -9. And that is equal to x to the 4th. And how do you get rid of this x to the 4th power? Very easy. We put both sides to the square root of x to the 4th right there. The same thing over here, x to the root of the 4th. And the function in the calculator is right here. So right there you have x to the somewhat look like the square root. So the way it works is this. Put a 4 right there, and you go shift, and you go that right there, and you just press the number. In this case, put the parentheses, 7.41 exp minus the 9. Group it with parentheses again, and what do we have? We have, of course, this will become x, and that becomes 9.3 times 10 to the -3rd. And that is the values of x, okay? So if we were to look for the concentration of hydrogen, that's pretty easy. Let me start right here. For hydrogen, Okay, well, let's do nitrogen first. How about that? Because we don't have to worry about that 3. Well, for nitrogen, it's just represented by X. So for N2, the concentration is very easy. It's just 9.3 times 10 to the negative 3 molarity. And that would be for N2. Okay, and what about for hydrogen? Of course, for hydrogen is represented by 3x. So we have H2, okay, and that's equal to 3x, and we know what x is in this case. We just plug it in, and that would give us what? So we take this times 3, that gives us 2.7 or 2.8 if we keep 2 acidic times 10 to the negative 2 molarity. And that is our concentration for hydrogen. Let's look at the concentration of NH3. Notice how we ignore the minus 2x over here. That only allows us to solve for the values of x easily without using the quadratic formula. But now we can find x, all you do is plug this in normally, minus 2x, which we know what x is, right? Is that number right here. So we can actually plug this into a calculator. 1.0 minus 2, 9.3 times 10 to the negative third. And that will give us our concentration for NH3 at equilibrium at the exact values. So 1.0 minus 2, 9.3 exp negative 3. That will give us 9.8 times 10 to the negative 1 molarity. And that would be the concentration of NH3. Now let's try a problem where we're going to apply this concept right here. That is, the K equilibrium, or the values of K, will only change if the temperature changes. So here we have a reaction above or below, in this case right here. And it is at equilibrium, okay? So at equilibrium, the concentration of HI is 2 molarity. And hydrogen is 0.1 molarity, and iodine is 0.1 molarity as well. Now what happened when I'm going to add 0.2 moles of HI, or hydrogen iodide right there, to the system? Of course that's going to mess up the equilibrium, right? Now you have what? In this case, if we look at this reaction, now you can have more of that. So, but the beautiful part is that it's adding to the same temperature. Because the temperature stays the same, that means the values of K is going to stay the same. It doesn't matter if you remove some of it or now you add some of it. So the question is, what are the new concentration of all gases once equilibrium has been re-established? So we just completely mess up the equilibrium by adding 0.2 moles of it. First thing first, we need to realize that we have to solve for equilibrium before we can really do anything. And of course, for any equilibrium expression, it's always Ke equal to the product over the reactant. In this case, it's H, and then we have iodine right there. There's no coefficient, so we don't have to worry about that. But down here we have Hi with a coefficient of 2, so that's to the power. And we know the concentration given to us right here at equilibrium. So we can actually solve for K at equilibrium. So this is possible because this concentration at equilibrium. If it's not, you cannot reduce it, okay? So be careful with that. It has to be at equilibrium. Since it is at equilibrium, let's plug it in. Do I know the concentration for hydrogen? Of course, it's 0.10. And what about for iodine? That's also 0.10 as well. Divided by hydrogen iodine right there. What do we have? Well, in this case, it says 2.0. So we have 2.0 to the second power. And of course, we can plug this into the calculator very easily. We have 0.1 times 0.1 divided by, group on the bottom, 2.0 to the second power, okay? And what do we have? Should I put this in decimal? Let's put this in decimal form. How about that? That makes our life a lot easier later on. This is where it gets tricky, because you know why? I'll show you why later. Okay, but fix the changes to decimal form. So we have 0.1 times 0.1 divided by 2 to the second power. So let's plug this into our calculator. We have 0.1 times 0.1, okay, and divided by 2.0 to the second power, give us 0.003. Okay, so keep that in mind. That is the values of k. Notice how this, of course, if we were to change that to scientific notation, that only give us 3 times 10 to the 1, 2, 3 to the negative 3. And this is larger than 10 to the negative 5th. So we cannot ignore the x in this case. So what does that mean? So now we go back and apply the changes. Well, first of all, if we apply the ICE method right here, ICE table, I is for initial. Initial, we now have a specific values, which is 2.0 m, okay? And for h, we don't have 0, but we have specific one, which is in this case is 0.10. The same thing for I is 0.10 as well. So that's a big difference, okay? This is happening at equilibrium. Now we're gonna add into it so that we are going to change it in a way that it is going to affect our equilibrium. And basically what we just do here is we add in 0.2 mole. And remember, molarity is equal to the number of mole per liter. So in this case we have a concentration from. But here's the tricky part. Remember we're adding that 0.2 mole? Where is that 0.2 mole going to go to? Is it going to go to the change? Is it going to go to the equilibrium? Or is it going to go to the initial? Think about it. You adding it, right? It's like you adding the reactant. Of course not going to be. It seems like it's going to be part of the change, but we don't know how much change is going to be. Because that change is always expressed in terms of x. So be careful. So instead of putting 2.0, it's actually 2.2 as your initial. That's your starting point. Even though you're just putting in, but still it is the changes of the initial that will affect to the changes in here, okay? So be careful with that part. Don't put plus 0.2 here. And now what we have here is, again, this will always be expressed in terms of x. That's why, that's another reason why we don't put plus 2 there. So here we have, what is it? It's of course going to be minus 2x. Then over here we're going to plus x, and here go plus x. So be careful with this. This is always expressed in terms of x, okay? Keep that in mind. So we have, at our equilibrium, we have 2.2 minus 2x. And here we have 0.1 plus x, and we have 0.1 plus x, okay? Or 0.10. I hate writing 0, so just keep that in mind. Alright, so now, what do we do next? Notice how we have that. That's what's going to give us a problem with that, because our equilibrium right here that we just solved for, 0.003, is a lot greater than 10 to the negative 5th. We cannot ignore this x anymore. So let's set up our equilibrium. Of course we have the same thing. This is our new equilibrium, okay? But again, equilibrium doesn't change because our temperature stays the same. Now the question is, how do we solve for x using this equilibrium? So we have, what is this? KEQ equal to 0.003 equal to, plug this in, which we know is 0.1 plus x, and this is also 0.1 plus x, and that's divided by the bottom number, which we know is 2.2 minus 2x to the square. And if we were to expand this polynomial, it would give us a quadratic formula. That's what makes the whole entire problem very difficult, okay? But if we look at this, look how beautiful this form set up. We have 0.1 plus x, 0.1 plus x. Can we just simplify that equal to 0.1 plus x squared? And look what we have. Square, square, to the second power, to the second power. See that? And this is just a number. It doesn't have variable to it. So what can we do to this problem? A very beautiful problem. Because if we have to the power of second to the power of second, what can we do? We can actually square root them all. And that would eliminate that. So what we have here is going to be 0.1 plus x over 2.2 minus 2x. But we have to square root that. So what do we have to do? Square root 0.003. And that gives us our answer of 0.055. There you go. Now we don't have to the second power anymore. So it's a lot easier, right? And the rest is just basically solving for x. Hopefully you have the algebra skill to do it. Of course, we are going to bring this over here and multiply that to that side. So which is 2.2 minus 2x times that. And we just distribute this in. Okay? Isn't that easy? So we have 0.1 plus x. And we distribute this in. Let me use my calculator just to help me out. Okay? In this case, we have 2.2 times 0.055, and that gives us 0.121. Okay, then we have negative 2x times 0.25. Oh, okay, so we have 2 over here, then we have 2x, then we have negative 2x times that number, then we have negative 2x times that number, negative 2 times 0.055, and give us what? Minus 0.10. Of course, x. There you go. Beautiful, isn't it? Now, can we combine like terms together? Of course, that's pretty easy. We bring this over here, and we bring this over there. So that way, we can combine the like term. If this is a negative, bring over. Of course, we're going to add, right? So let me use a different color to show it to you. So over here, I'm going to add 0.110x. But over here, I'm going to subtract 0.1. So keep that in mind. And what do we have in the end? So if this were to be adding, so we have 0.1 plus 0.110, which is okay. So we have 0.210x right there. But over here, we subtract. So we have 0.121 minus 0.1. That gives us 0.021. Can we solve for x? Oh, so easy. So we just solve that out. That cancel out. And what we have here is 0.21. And of course, that's already there on the calculator, divided by 0.21. Give us x equal to what? X is equal to 0.10. Or another 0. It doesn't really matter, okay? We can save that later. So what is the concentration of the equilibrium going to be? Of course, all we have to do is just plug in the values of x back into our problem. Now, let's focus on the hydrogen itself, okay? So we just plug this x over here. Well, for hydrogen right here, okay, let me use a different color just to make it look more stand out. So for hydrogen, which is H2, okay, we just have 0.1 plus x, which is another 0.100. Give us what? 0.20. Well, 0.1. It doesn't matter. Don't worry about suffix. Which is the molarity. And of course, the same thing for iodide too. So we have I2, which is what? 0.1 plus 0.100. Give us 0.2 molarity. And what about for HI? Well, of course we do the same thing. We just plug in the x. So for HI, okay, we have 2.2 minus 2 times 0.100. And let's plug into a calculator. So we have 2.2 minus 2 parenthesis 0.1 is 0, which give us what? 2.0 molarity. And those are the concentration at equilibrium. So again, for the HI or hydrogen iodide, we just plug it in the x values that we discovered here, and that's what we get. These are the concentration of the new equilibrium. Now do you see the complexity of this, when this doesn't work, we have to use the quadratic formula. But in this case, we got lucky because there's a pattern right here. We can get rid of that. But if it's not, well, good luck with that. Use your quadratic skill and solve for x. Okay?